I wanted to make a few comments today about non-determinism and Casper, and in particular, it's not even specific to Casper, but it's specific to our particular implementation of non-determinism, which I don't think I think the uniqueness of it slides by a lot of people. I think in many respects it shares something with quantum mechanics. Let me see if I can try to explain it. If you didn't know about RChain, and you didn't know about our node architecture, if I said there are all these nodes and they're all running computations, and the guarantee is that all of the computations agree, um, what would you conclude about whether or not the nodes were running deterministic computations? I think most people would come to the conclusion that the computations were deterministic or confluent at a minimum. Does that make sense? Do people understand what I'm saying?
Yeah, that'd be my guess.
Yes.
Yeah.
Or in the non-deterministic case, they're all executing the same part of execution, it's the same branch.
Yes. Yes. Exactly. Um, so but if they were non-deterministic but free of environmental influence, then you couldn't necessarily guarantee that. And that's the interesting thing, is that because of the consensus, we can have all of the nodes agree. They will all come to this, they'll all run exactly the same computation, but we have consensus on the races, and so they always take the same path. And that is as far as I can tell, that is a form of non-determinism that is not mentioned in the literature. No one, apart from RChain, has ever proposed this particular form of computation. And it's quite interesting because if you look at the way quantum mechanics works, it's a very, very similar kind of idea, in the sense that you have non-determinism, but everyone in the every observer in a light cone is going to come to the same conclusions about the way the resources get allocated or the measurements happen, which is remarkable. It's one of the reasons I have wanted very much to pursue quantum mechanics as a form of consensus. It's Go ahead.
May I ask you? I was following what Stephen Wolfram is doing, and he's saying that he's trying to understand a non-deterministic Turing machine, and his notion, and his notion, he's talking about multi-way execution. So I'm wondering, so. This is like a different, right? He's saying that in quantum mechanics, all paths are executed. And I'm not,
Well,
it's not clear to me.
no, but that's a particular interpretation of quantum mechanics, right? So that's the many worlds interpretation. So there are different interpretations that suggest that the ones that are not measured are not executed.
I see.
Yeah, but it really depends. But the funny thing about Wolfram is that he asked Bias to engage, and Bias. This is a John Bias, Mike Stay and Christian Williams advisor. So John was not so interested, but John actually recommended me to Wolfram, and Wolfram never got back. So he does not seem to have the bandwidth to consider the formalisms that are really going to help him out.
So maybe he's saying that he's now on like a 70s and non-deterministic Turing machine. So maybe later he will be more interested.
Yeah, decade or so later. Yeah, eventually he'll come around to understanding the formalism, the modern formalisms. In other note, I want to say that I got feedback, and the workshop was quite successful. We already have one student is interested in a sort of internship kind of arrangement. So it was very successful. We also got some positive feedback from at least one of the researchers. So hopefully there'll be more interest for this coming Thursday. Any questions that people have about material that we've covered so far, or anything else that we're working on?
Steve Ross Talbot is working on an addition to the webpage for academics that will give them some additional links and allow them to join a mailing list.
Oh, great. That's really good. That's a good idea. That's a very good idea. Go ahead.
I would like to mention, I was thinking about the creation of a Genesis block. And because we have non-deterministic execution, we need to share event log so that all validators agree. And I was thinking maybe we can, for a Genesis block, maybe we can execute rolling completely deterministically and say, in each race we will pick the first one or something that is always deterministic. And in that case, we don't need to share event log when we are creating the very first Genesis block. So this is like a special execution of rolling just for the first block, so that we can just put input parameters and all the validators will create exactly the same block.
Sure.
This is just like an optimization. And
sure.
What do you think?
Oh, I mean, does it gain us anything? So we're only talking about sharing the event log once.
It's it's simplified because then we can just every validator can create their own block, and when they agree that they're the same, basically they can start the network. So
sure.
Just simplify the starting of the network.
I mean, the simplest thing to do is to pick a particular computation. Right, a computation which you know to be deterministic. Then everyone can agree.
I was really thinking about that it would be nice that we have for testing that we have deterministic rolling, so we can always know how or we can test exactly the situation that we want. So I was also searching, how this can be useful maybe in normal execution.
Well, you can get completely deterministic execution if you do a compilation of lambda into row, right? So as the image of functions in row is the deterministic computation.
I see. So we will not create any race in that scenario.
Right. You can't, because functions don't have races, or more accurately, because lambda is confluent. So if you do have any races, it doesn't matter which path you take. The result will always be the same.
I found Agda proof that in sometimes lambda calculus can be non-confluent, and with this proof they are saying even if there is a multi-step in one branch, they can still see this as a confluent. I was a little confused why.
Yeah, that I'd have to see the details, because that's not. It may be a different lambda. You have to be really careful about what you're saying lambda is.
Okay.
Yeah.
Okay.
Okay. Any other questions?
Yeah, I have a question about this behavioral types and DeFi and the relationship. I mean, people keep to be, a lot of people keep pinging about, why are we not doing DeFi? If we do behavioral types, would that make us any safer for DeFi, or is there not a relation, and what does that take?
So DeFi is a security. It's not about whether or not the reason we're not doing DeFi is because you can't do it in the US. It's like, we would have the SEC crawling all over us.
I see. So it's a legal issue, not a technical issue. Otherwise, if somebody wants to do this in some other jurisdiction, they can do it now, or
do it now. Go for it. We don't, it's like, again, if they want to start up a shard and start doing DeFi, go for it. But
Okay.
We're not, as a co-op, we're not going to do this. And the reason we're not going to do this, and again, I don't think it's reasonable for the co-op to get into DeFi because it's not core tech. It's an application.
Yeah. Go ahead, Tomislav.
I just want to say that we need some role and code to support these different patterns, like for DeFi.
Sure. I mean, like the simplest, the thing that I think is reasonable for the co-op to get into would be a decentralized exchange. But even there, as a legal perspective, the issue is that we would have to apply for some kind of money changer license, some kind of broker dealer license. And that's expensive, time consuming, and would be distracting us from other stuff. But I do think that at a certain point, it would be reasonable for us to do a decentralized exchange. The design pattern for the exchange is for any kind of market making, streams of bids and asks is very much something that influenced the design of Rolang as a language. So it's very straightforward to do, market making in Rolang. It's a one-liner program. And so I would be, I really think it would be fun to implement something like that, just so that people get a sense of it. But I don't want to touch anything that is clearly and unambiguously a security. That's just
that makes sense.
That's begging for trouble.
Yeah.
Any other questions? Okay, then we can have today be a short one. I was just really, I think this idea of non-determinism, this particular flavor of non-determinism is quite intriguing. This idea that you can have non-determinism and agreement across all observers is particularly unique. It's not the kind of thing that you see written up a lot in the literature. So I think it's worth thinking about, and really letting it seep into your bones what the meaning of that is. But all right, we can call it here. And
I have one more question, if I
sure. Okay.
I was thinking when you presented square roots, and I didn't try it, but I was thinking, is it possible to use something like that for problem of dining philosophers, where we can somehow decide they're both like executing the same code?
Yeah, the problem is that when you form this cycle, like as long as they're sitting at a table and there's not one fork that they have to synchronize on, it's not a problem. As soon as they have to synchronize at a particular fork, you can certainly use it to get everyone to agree on which which party is going to be the party that picks up the fork first. So you could use it in that way. So yeah, that's an interesting thought. And you could, I mean, I really like Lerner's solution. Just add a footman who causes, who enforces a discipline on the use of the fork. But from a practical perspective, right? But yeah, if you want to get everyone to agree on the use of the shared resource, then the coin flip, the distributed coin flip solution will do the trick. Yeah.
I see. So they're not executing exactly the same program, but we want to have like completely opposite program in that sense.
I'm not quite sure what you mean. All I'm saying is, like, if they're sitting in a circle, right, then the issue is comes around to the last fork, because it's symmetry. It's at one point someone is going to be the odd person out. One philosopher is going to be the odd person out with respect to picking up the fork. One of the philosophers has to wait. And so you can get them all to agree on who is the waiting philosopher using the distributed coin flip. So yes, you can apply the nth root solution there.
I see. Yeah, this makes sense.
Yeah. So there's going to be a race on one of the forks, and they'll all agree on the winner of that race. Now, there's another piece of the puzzle, which has to do with fairness, right? Because in the next round of eating, they could all again agree. Let's say that Alice is the odd philosopher out the first time round. They could all again agree that Alice is the odd philosopher. Right. So over time, Alice is going to get skinnier and skinnier, and that's not the best solution. So it's not just about the agreement on who doesn't pick up the fork. You also have to have some kind of fairness so that no philosopher starves.
Oh, I see.
Yeah.
This is looks like some kind of oscillator. Right.
Well, it could, but what you really need to do is to get some kind of ripple effect so that it's not always the same philosopher, and like if you're actually working within real metabolism constraints, then you can't visit the same philosopher too frequently, right? So the distribution of who has to wait to eat has to be fair. Does that make sense?
Yes, and is this automatically means that we are storing some additional state because we need to track?
Not necessarily. No, you could ensure some kind of distribution of randomness. Like if you knew, well, maybe you're calling that a part of the state. I don't know. But I can imagine that there are protocols whereby you have a natural cadence, but that doesn't store information about the cadence.
I'm not sure that I know what is the cadence.
Rhythm.
Oh, I see.
Right. So there's a simple rhythm, right? First visit. So the first chair visit waits, and then the second chair waits, and then the third chair waits. So that's a natural rhythm, right? And you could also skip by any if you take any natural number that is relatively prime to the number of philosophers dining, and you skip that way, you're guaranteed to visit all the seats, right? So that's another rhythm, yeah. Now you may argue back to me, but that number, that the information necessary to do that kind of rhythm is additional state that you're storing. I mean, I'd have to think long and hard about whether or not you could devise it in such a way that there's no additional state. I'm not certain.
I see. Last time you explained how mathematics is. So you definitely opened my eyes to like thinking differently between mathematics and physics, and so I was listening Sabine, and she said that there is mathematics and there is science, and I mean, is mathematics is not part of the science, or only part of the mathematics that is applied to physics? So I was a little confused about that.
No, math is not science, right? Math is closer to art than it is to science.
Oh, I see.
So first of all, you can tell that math and science are different because, you know, in the modern theories of science, scientific theories are not provable. They're only falsifiable. Right? That's so someone puts forward a proposal about how something works, and because we can always be surprised by the physical world, right? There may be some element of our understanding of the physical world that's missing. So the best we can hope for in a situation like that, where we don't have perfect knowledge, is to find holes in someone's theory. So if we can't find any holes, right, and every time we probe it, we get better and better accuracy, that's a good indication that the theory is correct, but it's not a proof. It's like, you know, it's the equivalent of testing software. When you test software, you don't have a proof that it's correct. So scientific theories are only testable, they're not provable. And the reason is because we don't have perfect knowledge, right? There could always be some part of reality that surprises us. A new force, a new dimension, you know, yada, yada, yada.
Yeah, I was reading about neutrinos, how first they thought that they're massless, and later they found out that they're not, and this influenced the theory. And
yeah, exactly, exactly. So whereas mathematical theories are provable, right? So you set down what your criterion for a proof is, and that has changed dramatically over the centuries. What constitutes a proof has changed a lot, and we're still just scratching the surface of what we mean by proof. But as long as you have a crisp, clear criterion for what a proof is, then you can prove a mathematical theory. So that's the first dividing line for science versus math. There are other things. But the thing is, you know, the thing about mathematics is like designing a game. Like you get to come up with the rules and then you work within the rules, right? And as long as you, as long as everyone is, you know, playing in good faith and with goodwill in playing the game, then you can always check to see whether or not you're in conformance with the rules. But that's not how science works. So, but in that sense, this exploration of the design space is very much like art. Like with art, you're exploring a design space, but with art, you know, you often have other criteria. So like in mathematics, one of the criteria is aesthetics. So like Sabina, for example, she points out that the mathematical judgment of when a theory is beautiful may have nothing to do with the physical world.
Yeah, and in that sense, I was thinking, yeah, she's pointing exactly the you know, I understand what she want to say, But now I'm thinking, well, if mathematicians think about some theory, of course it must be beautiful. I mean, this is the part of design. So this argument that some mathematician looks for beauty, I mean, of course.
Sure, but it may not be the case that the physical world that we live in shares our sense of what is beautiful.
Yeah.
So that's where things get that's where things get weird. Yeah, but you know, like the other thing to understand is that there are more mathematical theories than there are real numbers. A lot more. So, you know, math is vast. And our exploration of the math design space is going to be a very, very small fraction of that. So you also have to ask yourself what invites us to investigate one part of the design space versus another. So the scientific criterion, whatever that criterion might be, that helps with the choices about what part of the design space to explore. The artistic criterion helps with a different, you know, a different region of the design space sometimes. Yeah, if you think about it, it's vaster than the multiverse, which is already very vast. And now if you think about the quality of our attention, you know, what within a human life, what can we explore in that vast space, and what will help us in determining which directions to go in that vast space. And that's where the connection between math and science and math and art starts to provide additional guidance. You know, if you know, I need to survive because there's a famine, can I use mathematics to help with a more efficient planting scheme, or, you know, a more efficient water collecting scheme? So all of those things start to impinge upon, you know, what region of the mathematical universe we explore.
Yeah, you mentioned once that like difference of what is like bigger, and how function space is much bigger than the value of functions. Like,
Yes, typically, unless you add additional constraints, right? So that's how. So if you think about it, I mean, these kind of cardinality arguments are old, right? So 2 to the natural numbers, is that the reals? It turns out it's independent of our known axioms of set theory. But for it is consistent to say that that is exactly the reals. So if you look at the growth, right, from the naturals to the reals, that's a big jump, right? So we went from naturals to 2 to the naturals, right? So in other words, all the functions from the naturals to 1 or 0. So that takes us to, you know, cardinality that's that can be associated with the cardinality of the reals, at least in, you know, if you accept, well, this has to do with the continuum hypothesis, right? So that's a gigantic jump in size, and so you have. But when you look at lambda, the domain of lambda values is equal to the domain of functions from lambda to lambda. So now you have to ask yourself, well, how could that be, right? Because the cardinality of the values from lambda to lambda is going to be much bigger than the cardinality of the values of lambda. And the solution is that you don't consider all functions, you only consider the continuous ones. Right? So that's the trick. So the hom gadget from lambda to lambda in the appropriate category is the set of continuous ones or the computable ones. And this trick of filtering on the hom gadget is what allows you to dance around this cardinality idea.
I was also confused about Hilbert Hotel paradox. And now I'm thinking that my confusion was mostly that I was thinking in terms of what is like computable or you know, can we write a program and you know like if we have this infinite hotel and we move all occupants on one room, I mean, this is not possible. But in this case, we are not talking about something like computable, right? That is like really, we can do it. This is just like some design space, right? As you mentioned. Not
Well,
like
I mean,
but don't think about real computing.
the whole point of countably infinite is that you can always take subsets which have the same size, right? And you know this from the natural numbers, right? So from the natural numbers, I can extract a subset which is exactly the same size as the natural numbers. The even numbers are in one-to-one correspondence with the naturals. So I could always move everyone over by one room, right?
Yeah. Yeah. Although this is not like, oh, I see. This is possible. We can just,
yeah,
we can just, this is like this splitting random generator, right?
That's exactly
You're
right.
just saying,
yeah. You're just, the thing is that the natural numbers is big enough that you can always bifurcate the state, and the two things, the two subspaces, you can always bifurcate the space, and the two subspaces are isomorphic to the original.
I see. And if we want to split in, oh, so this is why we can choose all the prime numbers, and then we are able to generate as like infinite splitting.
Yep, that's correct.
Oh, okay. That is something that I didn't understand, and last time you like bring me some some light to that. So now I have much better understanding.
Cool. Yeah, it's
yeah.
I mean, it's truly, I mean, if you think about the naturals, they're so strange, right? Because the naturals as a monoid under addition, they're generated by a single generator, right?
Yes.
It's one is your generator and plus is your operator, but naturals under multiplication is has an infinite number of generators, i.e. the prime numbers. And there's this strange, you can always compile multiplication down to addition. So what happened? What happened to generate that astonishing growth in complexity? Like just going from addition to multiplication, some magic thing happened. And nobody understands yet, right? This is like, if you understood what was happening there, you could probably find the zeros of the Riemann zeta function, and thereby win the Millennium Prize. So this, I mean, so like, this is what I was talking about when I was saying that the design space of mathematics is just so vast, right? We haven't even scratched the surface of the design space. And here we've run into a problem that's like 200 years old. The best mathematicians of many generations have broken their pick on this problem without real progress.
So this is why when you say that if we can sneak out a monoid, we can basically sneak out everything.
That's, well, yeah, that's correct. If you have a monoid, you're but I mean, there are other aspects of this monoid which are going to make it suspiciously close to. I mean, by the time you've brought in the naturals, which is what most people do when they're using a monoid with an effective equality, that's at least countably infinite. Then they've you've already brought in all of arithmetic, and therefore Gödel numbering, and you're toast, right? So that's why you have to you have to be very disciplined about what you import into that notion of names. But the nice thing is that you can be so disciplined that you just use what's lying around in your present moment, i.e. the theory of computation that you started with, and that's enough. And that's the same works for set theory with atoms and all kinds of other gadgets. So it's a technique that is that isn't just about the row calculus.
And when we have a row calculus, isn't it that we already have this monoid in the par?
That's correct. You have a monoid in the par. Exactly right.
So basically, we already have what we need, right?
That's correct. Yeah.
Okay.
And in fact, in general, even if you're doing SKI, you have enough structure to do what you want to do, right? Strings of SKs and Is, all that's sufficient to do what's necessary. So you can do a reflective version of SKI. Or of lambda is what I really mean to say. All right. Let's yield back 19 minutes, and I'll see you folks at the dev stand up in a little bit.
Thanks.
All right,
Thank
thanks
you.
to you all.